So we know that the dimension of r squared is 2, the dimension of r cubed is 3, and in general the dimension of r to the whatever is going to be whatever that number is. The dimension of r to the whatever is going to be whatever that number is. However, when it comes to span or a solution to homogeneous system, then things are not so obvious. For example, if we look at our earlier examples, we see that if I look at the span of these 6 vectors, it turns out that the basis only has 3 vectors. So that means as a vector space, this guy has dimension 3. And notice that number 3 has nothing to do with the number of vectors that I start off with, and it has nothing to do with the number of coordinates that I have either. Or in the next example, we find that the basis for the solutions to this guy has 2 vectors. So that means as a vector space, this guy has dimension 2, and we would not be able to tell from just looking at the matrix here. So in general, like let's say in part B, if I want to find the dimension of the span of these 2 vectors, I cannot just take a look at it and say, oh, I have 2 vectors, so it should have dimension 2. So this is not correct. And I also cannot just look at the number of coordinates and say, oh, it has 3 coordinates, so it should have dimension 3. So this is also not correct. So I need to find the basis and see how many vectors are there in the basis. For example, if I look at the span of 1, 0, then it's actually not hard to tell that the basis here is going to be just the vector 1, 0 itself. Or I can follow the algorithm. My A is going to be just the 1, 0 vector. A transpose will be, again, just the 1, 0. And if I were to reduce that, I get the same thing. So indeed, my basis will just be 1, 0, and because the basis only has 1 vector, so the dimension of this guy is going to equal to 1. And if we were to look at this, the span of 1, 0 is actually going to be just the x-axis. It's going to be this green line in the xy plane. And the basis 1, 0 will be this orange vector here. So notice that although I have a green line that lives in 2 dimensions, but because the line only has dimension 1, so the dimension of this space itself is going to be 1. Now for part B, my vectors are 1, 2, 3, and 2, 4, 6. Notice that the second vector is actually just 2 times the first vector. Now, if I were to use the algorithm, my matrix A is going to be 1, 2, 3, and then 2, 4, 6. And then my A transpose will just be 1, 2, 3, and then 2, 4, 6. Now I can reduce this guy, and that will give me 1, 2, 3, and then 0, 0, 0. So the dimension of this guy is going to be the number of vectors in the basis. It's going to be the number of non-zero rows here, and that is going to be just 1. So technically, what that means is the span of these 2 vectors, they are going to live in a 3-dimensional space. But it will only be just a line, so the span of 1, 2, 3, and 2, 4, 6 will just be, say, like a green line here. And the basis for this green line will just be the orange vector 1, 2, 3 here. So even though this green line lives in a 3-dimensional space, but the line itself only has dimension 1. Now let's take a look at the next example. If I want to solve this system of, well, I only have one equation, so this is not hard to see. My augmented matrix will look like this. My x will be the dependent variable, my y and my z will be the free variable, so my y can be anything, my z can be anything, and then my x is going to be minus 2y minus 3z. So then that means the solution as a vector, I'm gonna have that my x is minus 2y minus 3z, and then y can be anything, z can be anything. And I can rewrite this as minus 2y, y, and then 0, plus minus 3z, and then z, and then 0. Here, I separate the y with a minute, so this should be 0 and z. So here I have separated the y and z from each other. So then I can pull out y from the first vector. I'm gonna have negative 2, 1, 0 times y, plus negative 3, 0, 1 times z. So here, I'm gonna have that these two guys is going to be my basis. the set of solutions to this equation is going to be just all the linear combination of these two orange vectors here. And let's take a look at the visualization of that in the 3D coordinates here. So I have my x and y axis. So my mesh here, this is the xy plane, and then the blue axis here, this is the z axis. Now, if I look at the solution to x plus 2y plus 3z, which is what we have earlier, it's going to be a plane here, and the plane has dimension 2. So it makes sense that what we have earlier, the basis has 2 vectors. So this guy has dimension 2. Now, and the vector negative 2, 1, 0 and negative 3, 0, 1, if I were to plot that, I'm gonna have this guy here and then this guy here. So one of these, so it's a little hard to see, but one of my vector here, this is going to be negative 2. Okay, let's look at from here. One of my vector here is going to be negative 2, 1, 0, and one of the vector is going to be negative 3, 0, 1. Yeah, so these two black vector here will span the blue plane that we have, will span the set of all solutions to the equation x plus 2y plus 3z. And let's now take a look at the last part here. I'd like to find the dimension of the set of all solutions to this system. So if I were to try to solve this, I'm gonna have 1, 2, 3, and then 1, 1, 1, and then 0, 0 here. I can subtract the top row from my bottom row. So I'm gonna get 1, 2, 3, and then 0, negative 1, negative 2, 0 here. I multiply negative 1 to the bottom row. So I'm gonna have, let's see, 1, 2, 3, and then 0, 1, 2. Now then, I can subtract 2 times the bottom row from the top row. So what I'm gonna get is that my bottom row would stay the same, and then my top row would become 1, 0, negative 1, and 0. Let me actually kind of move this a little further down. This is the reduced row echelon form for my augmented matrix of earlier. So here, my x and my y is going to be a dependent variable, and my z is going to be my free variable. So my z can be anything. And then if I were to read out this equation, x minus c equal to 0. So that means my x is going to equal to my z. And then y plus 2c equal to 0. So that means my y is going to be just minus 2c. So the set of solutions that I'm going to have is going to be c minus 2c, and then just c here. Notice that I only have one free variable, which is c. So yeah, I only have one basis here, and that is going to be 1, negative 2, and then 1. So this orange vector is going to be a basis for my vector space, which is the set of all solutions to these two equations. And now let's take a look at that in the graph that I have from earlier. So let me kind of clear this out. So I have the blue plane, which is the set of solutions to the earlier equation x plus 2y plus 3z equal to 0. Now, if I were to introduce another equation, which is x plus y plus z equal to 0, I'm going to have another green plane here. So then, if I want the solution to both of this equation, what I'm going to get is going to be where these two guys intersect. So you can kind of see that they will intersect over the orange line here. So this orange line will be the vector space, which is the set of all solutions to the blue equation and the green equation. And you can kind of see that the basis for my orange line is indeed going to be this vector, this black vector here, which is the vector 1, negative 2, and 1 that we have seen earlier. And the dimension of this orange line is going to be 1, and that's because I only have one basis here. So for the last part, I only have one basis. The dimension here is going to be 1. And that kind of makes sense because a line has dimension 1.